All right. Hello, everyone. Can I have your attention back to the class? Okay. Happy Wednesday, and today's Wednesday, right? And welcome to another class, Next 463. Let's continue with what we started last day. We were solving some simple single-degree freedom free vibrations, right? Again, as I said, always remember that category that we, at the beginning of the class, we draw together. We are still in single degree of freedom, which means either we have variable x or theta or y, just one variable. So it means one equation. And it is free vibration, no excitement, no external force, and there is no friction or no damping. It is just mass and springs. But they come in different form, like in this shape, which after we draw the free body diagrams, we ended up with an equation which looks like our original equation, which we had for a mass and a spring. If you recall, for a mass and a spring, we ended up with the equation which looked like mx double dot plus kx is equal to 0, right? That was the original equation. And obviously, it was for a system which it had one spring and one mass and k. So we work with that equation, and always we work with this equation, but any other equation that we end up, like for this system, is going to be something very similar to that. And some people prefer to use like m equal and k equal here, like equivalent mass and equivalent stiffness for any other system. In that case, our natural frequency here, we find that it is k over m. And as you saw here in this example, 9m is the mass of this system, and 5k is the stiffness of this system. All right? So whatever is the coefficient of, let's say, x double dot or theta double dot is the mass of the system, and whatever is the coefficient of the variable, here theta, is the stiffness of the system. Okay? And based on that, we managed to find the natural frequency, which is the square root of 5k over 9m. Right, so here then, we would say these two systems are like equivalent of each other. So their behavior will be the same, like the mass and spring with k equal, which in this case for us, the equivalent stiffness is 5k, and the equivalent mass is 9m. So these two systems are going to behave vibration-wise the same natural frequency. Later when we have external force, they're going to behave the same. So let's solve another example very similar to this one and find out what is the equivalent mass and equivalent stiffness of the system. Okay, so it's a upside down pendulum with two springs, and the system is at equilibrium position in the position that's being shown. Again, we start always these three steps. First, we start with the kinematics, figure out how this system is going to move and vibrate. So it's obvious, it's a pendulum, upside down pendulum, join at O. There are two springs, and if there is any vibration or motion in this system, it's going to be left, right, swinging left and right. So the kinematic is obvious, right? The second is figuring out what is the best variable for this system. So obviously, since it's a rotation system, then theta would be a good choice. But again, as I said, you may go with the x and y and find a relation between x and y for these mass. And whenever there is no information for the bar, it means the weight was negligible. So here we just have a pendulum with no bar, the particle mass m. Because then the question didn't tell us anything about the radius of this ball. We can assume it's a particle. Obviously, for the sake of free body diagram, I showed this deflection large. However, since we are in vibration, the range that we are talking is it's going to be around 1 or 2 degrees. But that's okay for just showing it to showing a large like deflection. So this is our variable. What we did, we moved this system and disturbed it from its equilibrium. Right, so we ended up with this new system. And then the second step, the third step is to, the second step is to draw the free body diagram for this system. When we want to draw the free body diagram, always we need to ask this simple question. Because of the weight, is there any pre-compression or pre-tension in the spring? So when it is at equilibrium, so this is when it was at equilibrium, this was the weight, right? The weight comes directly past 2.0. So it does not have any effect on the springs, right? It means there is no pre-compression or pre-tension in the springs due to the weight. In other words, there is no delta static in these two springs. All right. So it means the weight hasn't done anything to the springs. When this is the case, we should include the weight. All right. Otherwise, if because of the weight there is some delta static, it means that they are going to cancel out each other. As I showed in the very first example that we solved together, we included the weight and delta static, and you saw they cancel out each other. Right? So there is no delta static. Then if there is no delta static, I know that I have to include weight in my diagrams. So the free body diagrams, then when I deflect it, we draw the free body diagram for the case when it has been deflected. So I have the weight, that's mg, right? And then we have two springs, left and right. So obviously we know the springs, the one on the right has been compressed. So I will have like a force to the left because it resists the motion of this pendulum. And then I have a force, right, which is tension for the spring on the left. That's again something it's easy to realize. And what is their deformation? We talked about it and we said because we are in vibration, the motion are small, so the deflection of this one is going to be b theta, and the deflection of this one is going to be again b theta. So that's my free body diagram. I'm not worried about point O because it's just a point, and we just draw it for the sake of showing the force. In future, if we are interested to design this pin, maybe we can find OX and OY. So we have the free body diagram, then simply we use the Euler law. Euler law says if you have a rotating system, sum of all the moment about that point must be IO alpha. Alpha is the angular velocity of this system. So something that I said you need to be careful when you take the moment. So in a static or in mechanics of material, we had this convention that counterclockwise is positive, clockwise is negative, but here is a little bit different. whatever variable that we choose, like theta, and we show it in our diagram, like this one, that's our positive direction. So maybe you draw the same three-body diagram, but initially you deflect it to the left. That's totally fine. Okay. So for me, this is the positive direction in order not to forget. So why not I show it over here by this sign? To just remind myself, remind the person who read my notes that the clockwise for me is positive. Why? Because I choose theta to be positive in that direction. Let's take the moment about point O. So about point O, what do I have? I have minus k b theta multiplied by b, which gives me b. Again, since it is vibration, although it's being oblique and the vertical distance is not exactly b, but because it's very, very small, it's okay. We can approximately says that the distance, the vertical distance is b. So I have another one, k b squared theta, right? One on the left, one on the right, and they are trying to rotate these things counterclockwise, right? These two forces try to push these things to the left and rotate it counterclockwise. Then I have mg. mg try to rotate it clockwise, try to bring it down and rotate it clockwise. So it is then positive, and the distance that I have is going to be L sine theta. Right? This is the distance that we need to figure out. If I show it over here, in this triangle, this distance is simply L sine theta. We could have done the same things for this b, write down they are b cosine theta, but we know that, right, the vertical distance, or let's say the actual moment of the springs is k b theta, right? The force multiplied by the distance, which is b cosine theta, right? The vertical distance is b cosine theta. We're talking about this distance, like in this triangle. After they have been deflected, now the distance is b cosine theta. However, we said that cosine theta in this course, we can approximate it by 1. Right? Similarly, we can approximate sine theta by just theta. This is what we said at the very first session. Anyway, my point is you can still use the actual distance, but you ended up with summarizing them and get rid of cosine theta and sine theta. And then it is equal to IO, which we talk about it for a particle. The moment of inertia is just mass, the distance squared, and alpha for us, our variable is theta. So alpha here is theta double dot. Right? So alpha angular velocity is theta double dot. If I simplify this equation, I would get ml squared theta double dot plus mg minus 2k, write it down a little bit below, 2k b squared theta equal to 0. Yes. So mg, let's take a look. Mg is trying to rotate these things clockwise or counterclockwise.
When you subtracted it to the other side.
Oh yeah. We move everything to the other side. So this is negative, this is positive. So thanks. So this is 2k b squared minus mgl, right? We have also. Now it's correct. So this is our equation of motion. For us, this is the equivalent mass, and this is the equivalent stiffness. No matter what they have or what their unit is, in some problem we may simplify them. For example, we may divide them by L squared. So this one looks like more like mass, but it doesn't again matter, because eventually we are interested in knowing the natural frequency of this system. And the natural frequency is always is k over m, or k equivalent over m equivalent, which simply for us, it is 2k e squared minus mgl divided by ml squared. So this is the natural frequency of this system, right? And again, as I said, you can divide like the numerator and denominator by L squared, by M, simplified it, doesn't matter. That's why in our original equation, you are allowed to leave it as it is, or maybe divide both sides by L squared, divide them by M, whatever you do, make it simplified. So this is the natural frequency. Now I have a question for you. If I build this system, let's imagine you build this pendulum, okay? Try to visualize it. You build this pendulum, and you happen that you didn't do a good design, and maybe the pendulum that you built is very long. Let's say it's very long. So this is like where you pin it to the ground, and the stiffness that you purchased to build this pendulum, they are very weak, like K and K. So let's say their stiffness is very small. So do you think if you disturb this system, so again, visualize that the length of this pendulum is very long, this mass is heavy, like a large M, and the stiffness are very weak. Okay, so this, or very small stiffness. So what will happen if I, let's say, disturb this system a little bit? So you show it by hand. What will happen? Yeah, it just go over, falls off, right? It's not gonna, there is not enough force to bring it back so the system can vibrate. So one conclusion that we can make, if I have a system that is at equilibrium, like this system, it's not necessarily, and I have a spring and I have mass, it's not necessarily it's going to be a vibrating system, right? Like as you can see here, if you can visualize it, if you build this pendulum, the stiffness are weak, you disturb it, so it's just going to fall off, right? You disturb it a little bit, let's say over here. And then the weight is heavier than what the stiffness can handle, and it's going to fall off. So how do we know our system is going to be a vibrating system? What criteria we can have? So how can I control? Let's say I'm designing these things, and I like this system to be a vibrating system for maybe an application later. What do you think we can impose on this system to make sure that our design is okay? So let me repeat the question again. So you realize that for the system at the bottom, right? Because of a bad design, if you disturb it, it's going to fall off. It's not going to be strong to return back. But we are in charge of designing this system, and now we need to pick a stiffness, we need to pick the length of these things, we need to select the mass, and we like this system to be a vibrating system. Maybe we are building a toy for kids, and So what should be the criteria to make sure that this is a vibrating system? Yes, I'll...
Natural frequency larger than 0.
Exactly. Yeah. So you look at the natural frequency. In order for these things to exist, we like to have an omega n, right? Because omega n guarantees a harmonic motion. And if I want a harmonic motion, then it means this has to be a real number, a number bigger than 0, and to be a real number bigger than 0. So this guy has to be bigger than 0. So, right, to have a harmonic motion, (2kb squared minus mgl), right? It has to be bigger than 0. So that's our criteria. So you can now figure out that k, for example, has to be bigger than mgl divided by 2b squared. So your stiffness that you choose, let's say you are constrained by the length, you are constrained by the mass, but you are free to choose, like to buy any stiffness that you want, any springs that you want. So you go and pick a stiffness or a spring that has a stiffness bigger than mgl 2p squared. Then, of course, later we will get more to the detailed design of these things. And this is where we need a certain frequency. For example, you like these things to vibrate, but also how fast you like these things to vibrate. Let's say you make a toy and you want the vibration to be in every, let's say, minute to be 100 times go back and forth. So you have omega n, you have some information to complete your design. In this scenario, what we say the system is stable. System is stable. Previous system wasn't stable, right? If I disturb it, it's just going to collapse, not getting back to its equilibrium. But this system is, this is the terminology we use. We say it is stable. It returns back to its equilibrium. And something that people use a lot to demonstrate these things, this stability and not stability. Let's say I have maybe these two curves on the ground, okay, two curves on the ground. And if I put a ball in the middle of each of these, okay, two curves, one upside and one downside, left and right, and I put a ball at the center of these two. So both of these systems are at equilibrium, right? So it is at equilibrium. Right? This is also at equilibrium. They are staying there, they are not moving. But you know, if I disturb these two systems, the one on the left, if I disturb it, it's going to swing, come back to its equilibrium and swing left and right. But the one on the right, it's just going to move and never come back. So we will say this system is stable, and this one is unstable. In vibration, we want systems that are stable, right? Otherwise, it's not vibration. It goes and never come back. And this stability is one of the criteria when we design the vibration or dynamic system, because we want them to return back to equilibrium. Any question for this part? Are we good? Okay. So that's great. Please review these two examples, example 5 that you just saw, and last Monday example. So the difference between these two was this including the weight and not including the weight, which at the very beginning of the course we talk about it. Pay attention if there is retention or compression in the spring. So here In my diagram, there is nothing. We haven't talked about the weight, because the weight has been canceled by the static deflection. And in this one, we included the weight. Right? Intentionally, I put these two examples next to each other, so you realize when you should include and when you shouldn't include the weight in your diagram. It doesn't mean that we are ignoring the mass in previous example. It is, as I showed before, it is that if you include them, you need to also include the static deflection in the springs, and they eventually cancel out each other. I leave these examples for you to solve later at home. It's very easy. I just draw the free body diagram. So I give you 30 seconds to read it and figure out what it is. All right, so I guess it's obvious. We have a pendulum, and this pendulum has a torsional spring at the top, right, at the pin, which resists the rotation. So with torsional spring, we know it's going to create a moment opposite to the direction that we choose. So we disturb it to the right. So this spring is going to create a moment which is KT. We use the letter T to emphasize that's a torsional spring. KT theta, and obviously I need to include weight here, right? Because at equilibrium, the weight didn't do anything for the mass or didn't create any deflection for the mass. So that's my free body diagram, and this point, of course, is the center of gravity for this slender bar. So I have all the information that I need, the distance. For example, here, so I have this distance, which is L2 sine theta, right, in this triangle. So I can easily write down the sum of moment about point O is equal to IO alpha. Let me quickly write it down, but then you can check it. So the positive direction for us is counterclockwise. Again, don't forget the positive for us in this course is the direction that we choose. Like here, this is theta counterclockwise, and that's the positive. So then I have minus KT theta. That's a couple, that's a torque. So I don't have to multiply by distance. It's already a moment. And then I have mg. Mg also is the opposite direction, right? So minus then mg half of L sine theta. And for a slender bar, we discussed that the mass moment of inertia is 1/3 m L squared. Remember, 1/12 was for I bar. So a slender bar, its I bar is 1/12 ml squared, and at one point it is 1/3 ml squared. Do not mix them up. So 1/12 for the middle, 1/3, one of its two ends. Theta double dot. So you get rid of this sine theta by replacing it by theta, and then the rest, just simplify the equations, and it's obvious. I believe it's simple. Anybody has a question? So you should be comfortable with then this topic so far. I hope your TA also explained things for tutorial 1. So far, again, a single degree of freedom system, you should be able, when you look at the mechanical system, realize how it's going to move, the kinematics. draw the free body diagrams, and then write the equation of motion. Either draw the free body diagrams and then use Euler's and Newton law. Yes.
Should be over 2 squared.
When you take the moment for weight,
Yeah.
so that's the force, right? Mg multiplied by the distance. So the distance is L over 2 sine theta. That's correct. Yeah. Yeah. So the weight multiplied by the distance, which here, and the unit seems to, yeah, the units also are there. All right. So, and the second method, which is the Lagrange method, also you should be comfortable using the Lagrange method as well. Please try to get the same equation using the Lagrange equation. So the first one is the Euler. And do it on your own and see if you get the same equation after you simplify everything. And then find the natural frequency from these things. Do it on your own. So, assuming that you are comfortable with this topic, now let's add a little bit of excitement to our system, which is a little bit more exciting. So, again, going back to the diagram at the beginning that we had, now we are adding external force to the system. So rather than having a free vibration, our system now is going to experience some sort of excitement. But the very first excitement that we are going to apply to a system will be a harmonic excitement. And by harmonic excitement, it is either cosine or sine at frequency multiplied by t, like f0 cosine omega t. There is no difference if it is cosine or sine because they are a harmonic motion. And for us, it doesn't matter. It is just at the beginning when we apply the load. But since this system are going to vibrate for a long period, it doesn't matter if it's sine or cosine. You will see in the equation soon. So this force, again, later we will deal with forces that they are not harmonic. But at the very beginning, we are dealing with system. We are adding excitement to this system, which that excitement is harmonic. And when people talk about these forces, they talk about the force, they say they refer it, they use this terminology. We apply a force with this frequency. So when they are referring to this omega. Right? This F0 is a constant. For example, I can apply, so this force should be over here. For some reason, mine is wrong. So let's let that go. Okay, so that's the force. All right. So this force, for example, it can be, let's say, 100 cosine 5t, and the unit Newton. Okay. So the constant force, frequency 5 hertz, right? 5t. It means I'm applying a force, and in 1 second, I'm repeating it 5 times. So that's a harmonic force. And our goal is to study the behavior of this system. So, like always, we start with free body diagrams. All right? A very first question that we need to ask, is there any pretension or precompression in this system? Forget about this force. System is at equilibrium. Is there any pretension? We say yes. Because of the weight, there is pretension. So when I draw the free body diagram, I don't need to be worried about weight. So let's draw the free body diagram here somewhere there for this system. And again, we forget to choose, we coordinate. So since this system goes ups and down, at equilibrium, before I apply any load, well, let me show it on the other side so you don't get confused. All right. So before we apply the load, let's say that these things was staying at this point. It was my equilibrium, and I choose like variable x, or you can call it y, as my coordinates. So that's the coordinate, that's the force, and now I can draw the free body diagram. So I have an external load. That external load is Ft, whatever function it is. And then I have, of course, a spring, which is Kx. So I assume that the system, I disturb it by x because of now this force. So this is my free body diagram. So that's the free body diagram. So the Newton law simply says sum of the forces is ma, because it's a particle. We don't need to worry about the moment. So the forces that I have in x direction is, so all of them in x direction, it is minus kx because it's the opposite direction, plus ft m, and my acceleration here is mx double dot. If I simplify everything here, I will get mx double dot plus kx is equal to f0 cosine omega t. And I replace ft by the original function. So now this is my equation of motion. As you can recognize it, the first part on the left is exactly similar when we had free vibration. Now on the right, we have extra term, which is f0 cosine omega t. So we need to solve this problem, right? This is a second order differential equation. Hopefully you remember how to solve it. But if you don't worry, the level that we need is as follows. So if you recall, when we deal with this equation, which the right side is not zero, we say the answer to this equation has two parts. The complementary part and the particular solution, right? So we show them by xc and xp. Complementary solution. And this one is the particular solution. So for the complementary solution, what we do usually, we say mx double dot plus kx is equal to 0. And we find the answer to this one, which we did before. We find that xc, like the answer to this one, is a cosine omega nt plus b sine omega nt. This is what we found before when we deal with this complementary part of this solution, right? And we show it by x. Omega n, we know what is omega n, is k over m. So the natural frequency is not going to change, although I have an external load. Natural frequency is the natural frequency, depends on the stiffness and mass, and it's going to stay the same. And the equation also shows the same things. Now for the particular solution, we have to guess an answer. So I have mx double dot plus kx is equal to f0 cosine omega t. We need to guess an answer. So this is how we solve the differential equation, if you recall. So if I look at this equation, what should be a good x? So what is a good function? So I have cosine omega t, right? So I need something that when I take the derivative 2 times, and here the same function, I could get rid of cosine omega t. So let's start by a guess, call it x, capital X, cosine omega t. This is what we guess should be the answer. So this capital X is a constant, which we don't know what it is. We don't know if this can be the answer, but we just guess. Now what I need to take the derivative 2 times, so x dot then will be minus x omega sine omega t, and x double dot will be minus x omega squared cosine omega t. If we substitute them there, so I will have minus m x omega squared cosine omega t. So we are substituting them, right? And then I have minus kx, which is x cosine omega t, right? And then on the other side, I have f0 cosine omega t. So cosine omega t, I can get rid of them. So and find is x, which is f0 k minus m omega squared. Okay, so this part, we call it xp, right? A particular solution. And xp we found is this capital X cosine omega t, and x we just found that has this form. So now I need to put these together. So I will have then xt is xc plus xp. Of course, they are a function of time. I was just lazy and I didn't add tn for them. xc is a cosine omega nt plus b sine omega nt. And xp is f0 k minus m omega squared cosine omega t. Let me write it down on my next slide. So the xt, the solution that we were looking after, is a cosine omega nt plus b sine omega nt and plus f0 k minus m omega squared cosine omega t. This is the solution. A and B are constant, which similar to the free vibration, we need to find them based on initial condition. Let's say I have like initial condition let's say at time t0, xt will be x0, and at time t0, let's say x dot t is v0. Like a general case, I have x0 and v0. If I substitute them, simplify everything, so I would get xt x0 minus f0 k minus m omega squared cosine omega nt plus v0 omega n sine omega nt plus f0 k minus m omega squared cosine omega t. So in fact, this is our A that we found, and this is B. Not be afraid of this long equation. You can try it once and find this A and B, and you can always use it in this form. It's common to just use the final answer. You just need to substitute the values there, but you need to know where it comes from, right? Any of these can be zero. For example, maybe in one question, you don't have V0 or you don't have X0. And these are given by the problem. So we have V0 and X0, initial condition. We have the external load. And then K and M are, we know them. So we know natural frequency. So then we have the final answer, how this system vibrates. All right. So I want you to just pay attention to this one. One thing that you should be careful is this system has sine and cosine, and their frequency is different. Like this one is omega n. Omega n can be any number, depends on k and m, right? Because remember, omega n is k over m. So that's the natural frequency. And also this system has omega. So this one is the forcing frequency. That's the frequency that we force the system to vibrate, right? So this function, I like you guys to go home and until Friday, we use MATLAB or Python and plot it. I upload a MATLAB function, short MATLAB code to plot these things. On your notebook, it says also try to download that file, run MATLAB with different omega, because next Friday, on Friday, next session, we're going to discuss this function. And it would be great if you just plot these things. You don't need to spend too much time, just it probably takes 5 minutes from you. Download that file. And as I said here, just change this value of omega. Change it to 5 hertz, 10 hertz, 100 hertz, and see what we have. Thank you for listening. And again, as I said before, if you have any question outside that door, because I have to leave, be ready for the next teaching.